Okay. Hi, everyone. Welcome. Welcome again. Okay, so today we're talking about RAID. So RAID stands for Redundant Array of Independent Disks. So this is going to be, this week we're doing storage. Next week, we're going to continue and start talking about databases. But today we're still doing storage and how to leverage storage in the context of databases. So, okay, so what is RAID? So RAID is designed to address 3 problems. Okay, and here are the problems. So first of all, in the previous lecture, we looked at disk drives or SSDs, but your database might exceed the capacity of a single storage drive. Right? So you might want to store your data on multiple drives. So how do you kind of do that smoothly? How do you kind of scale your data size across multiple storage devices without kind of doing anything too manual? Okay, so that's the first problem. The second problem, as we saw last time, our drives might fail. Right? So with disks, we saw that 1% of all disks in a system might fail in a given year. We also saw that SSDs die as a function of the number of writes that you issue to them. Right? So both disks and SSDs are going to fail. So we need to be able to deal with those failures, and RAID is going to help us deal with storage failures as well. Okay, and the last problem is RAID is going to allow us to actually go beyond the performance limitations of just a single storage device. Right? So if your system is using a single disk, right, it's going to have very, very limited bandwidth. But if you scale your database across multiple disks, you might benefit from the combined performance of all of these different drives. Okay, so these are the 3 motivations for RAID. Any questions about motivations? Okay. So RAID actually originates from this nice paper from '88. Okay, so this has been with us for a while, and this is a very classic paper, but worthwhile knowing where it comes from. And here is basically the main idea. So RAID is going to divide data from our database across multiple storage devices, but it's going to make all of these storage devices look like a single storage device to the application. Right? So it's basically hiding all the storage devices behind some abstraction that looks to the database or looks to whatever application is running on top as one storage device, but there are actually multiple storage devices underneath. Okay, and in some sense, right, so you can kind of look at it like this. It's so here we have these 2 disks, right, each with n bytes of data. So across a RAID interface, these 2 devices will be exposing the combined capacity, right, of both devices. So here the capacity is 2n. And right, this looks like a single storage device to the application running on top. There's going to be some complexity, right, across on the other side of the abstraction, but at least this is the abstraction. Okay, good so far? All right. Okay, so RAID can actually be implemented in hardware. So here's an example of what this might look like. So you might actually have a RAID card that multiple storage devices are connected to via wires, or you could also have software implementation of RAID, right? So there's a Linux MDA VM utility that you could use to actually create RAID artificially or using software across multiple storage devices that are plugged in. There's going to be some performance differences and cost differences, but it's both just RAID. Okay, so we're going to cover 5 kinds of RAID designs in this lecture. Each one of them is going to have, different idiosyncrasies, different trade-offs. We're going to learn to kind of, appreciate them, see what each one of them means. All right. So let's get technical. So the first one is called RAID 0, or just pure striping. So this is pretty simple. This just says that if this here is our logical address space, right? So each one of these addresses represents, let's say it represents some unit of storage. Let's say it represents a 4 kilobyte chunk of data. So what RAID is going to do is it's going to stripe adjacent addresses across the different storage devices, right? Such that if we're actually writing across the address space sequentially, right, the writes are going to go, in this case, we have 4 devices. So the writes are going to go 4 at a time to each one of the drives, right? It's nothing too fancy, right? But it's perhaps the most straightforward design you might come up with. Okay, so now we might ask some questions about how this thing behaves. Okay, so we might first of all ask, what kind of a bandwidth boost do we get for, let's say, sequential reads or sequential writes with respect to the number of drives that we're hiding under the RAID? The answer should be straightforward, yes. 4 times in this case, but yes, and generally we get a sequential boost equivalent to the number of storage devices that we're hiding. How about random reads and writes? Here I'm not expecting like a precise answer, but will this improve the performance of random reads and writes if our application is issuing them? Okay, let's let somebody else, but if not, I'll come back to you. So will things be better or worse? Yeah. Okay, but for a read, we only actually have to go to one of them, right? So, suppose that I want to read address. So you say I might have to go to multiple? One?
Maybe
okay, but if I need to go to multiple and I'm looking for different addresses, and I can do it in parallel, right? Okay, and that's actually precisely the point. So this is actually also better for random reads and writes because you have a degree of load balancing, right? So default, you could have like a terrible situation where you're asking for address 1 and 5 at the same time, and they happen to be on the same disk. In this case, you cannot really get any parallelism, right? But in the general case, if you have random reads and writes, you can kind of parallelize them across this as well. So that's nice. So you get this improvement as well. What's the problem with this? And you have hints on the slide about the core fatal flaw of this design and the reason it's not actually used in practice by almost anybody. Yes? There's no redundancy, which means that if failure happens, we lose data. Okay.
Oh, why there's like 0.4 instead of 0.1?
What here? So it's 0.4 because because we're doing striping, right? So basically addresses, right? So addresses 1, 0, 1, 2, and 3, right? Go to disk, to this, and this one. And then, we begin the stripe again, right? So we begin the stripe. So we go back to the initial disk and we write another stripe. And each stripe consists of 5 adjacent addresses in the.
This is like 0, 1, 2, 3.
Yes.
Writing sequentially, so it's right throughout this and something else you again.
Yes, I think we got it. Does everybody kind of get it? Okay. Okay, so basically, we covered the pros and the cons. So in some sense, this design is at the extreme because it's kind of as good as you could possibly be in terms of performance, but it has no redundancy, so it's as bad as you could possibly be in terms of fault tolerance. Okay. Okay, so let's move to RAID 1. Okay, so with RAID 1, we have, okay, so we call this mirroring. And this is in some sense the other extreme. This is a design that is prioritizing redundancy as much as possible. And it's just, right, taking the data and kind of duplicating the data or mirroring the data across all storage devices that you have. Okay, so there are some subtleties here when we look at, analyzing our different performance metrics. So, okay, so first of all, sequential writes. Are sequential writes going to be faster or slower relative to if we just had one drive? Yeah. Yeah, it's going to be the same. What about sequential reads? Sorry? Was it about the same? Okay. So that's a nice intuition, but actually reads can be faster. All right, so yeah. Exactly. Exactly. Yes. So sequential reads can actually still benefit in terms of bandwidth from the combined throughput of all the different devices, even if writes cannot. Okay, which is okay, an interesting subtlety. So we're going to use a Sensite for the other RAID designs as well. The fact that we can sometimes get a higher read throughput, even if our write throughput is kind of so good as it can be. Okay, and in terms of storage capacity, clearly we're wasting most of our storage capacity. Okay, good. Okay, so now we've kind of seen two designs that are as good as could be in terms of performance, right? And we've seen one design that's kind of kind of goes to the max in terms of redundancy. Does anybody have a sense of how we might combine them?
Maybe like some overlaps between.
Yeah, that's a good intuition. That's a good intuition, and precisely what RAID 0 plus 1 strives to do. So this is just a very straightforward kind of taking, combining both of these ideas. You see, this is this is our address space here. So here, basically, we're doing striping, right? So we're doing striping with respect to, this first drive and, this third drive here. But furthermore, each of the drives is still mirrored, right? And this means that if one of them fails, we can recover, or, our system doesn't get stuck, we can replace the drive at least, and then recover the information on the new drive. Okay. So let's assume we have n drives in our system, and let's assume that there are x mirrors per drive. Right? So if x is equal to 0, we basically have pure striping, but if x is equal to 1, right, we have duplication for each drive across one drive, right? So okay, so I'll just sort of give you some of the answers. So okay, sequential writes are going to be they're going to be penalized, right, by this factor. It's the factor of kind of the proportion of mirrors that we have. Right, so we can't benefit from the combined throughput of all the different drives because some of them are just dedicated for mirroring, right? So we basically just detract the effect of the mirroring from our combined write throughput. How about sequential reads?
A little faster.
A little faster?
We can parallelize, like there's a little bit of parallelism before.
Yeah. So can you be more precise about like the kind of throughput that we can get with respect to the number of drives? 2 times? 2 times what?
More.
2 times? No, I mean, suppose we have 10 drives in the RAID. So will the factor still be 2 or? So what is it with respect to the number of drives that we have in the RAID configuration? Yeah. So it's still going to be the combined bandwidth of all the drives. Sorry, what did you say again? Okay. Okay. Yeah. So it's still the combined bandwidth of all the drives because again, you can do kind of the read reordering, right? So imagine I'm trying to read 0 to 4. So then the question is, how can I kind of parallelize the request 0 to 4 across these drives so I can read all of them at the same time? Right. And what I could do is read 0 from here, 1 from here, 2 from here, and 3 from here. And I can do all of that at the same time. Right? So if you're doing that kind of reordering, again, you can get the combined throughput of all the drives. Yes.
What do you mean just one read 0?
Mhm.
What do you mean just one read 0?
So that's kind of, sorry, sorry?
That's kind of like the corner case.
It's not a corner case, it's a valid case, right? This happens sometimes. So, so here I'm talking about sequential reads and writes. What you're talking about is a random read, right? The random read is one that reads a small unit of data.
Yeah.
And for random reads, for random reads, you're not going to be able to benefit probably from the combined throughput of all the drives. But random reads are still going to be better using RAID because you can still achieve some degree of parallelism. Does that make sense? Right. So for random reads, you could, so suppose you try to read, so if reads are nice and sequential, you can kind of reorder them to kind of benefit from the throughput of all storage devices at the same time. If you have random reads or writes, you might happen to have, a stream of writes or reads that, target one of the drives disproportionately. In that case, you can benefit from the combined throughput. You're still better off than if you use a single drive, but it's not as clean as in the case of sequential. Okay. So far, all these designs are kind of intuitive. Now things will become a little bit more interesting. Everything with me? Everybody with me so far? Okay. So here I'm actually kind of giving you a notion of how we might handle sequential reads at the combined throughput of all of them, right? So here, imagine that we have a sequential read right across the design space. So we're reading addresses 0, 1, 2, and 3. Right, so here is, right, so to do this all in one time unit, we might read, right, 0 from here, 2 from here, 1 from here, and 3 from here. We order them and return them back to the user, right? And then we might continue here, right, and read addresses 4, 6, 5, and 7 at the same time. Okay, yes. But with this, we're still wasting a certain amount of our storage capacity. All right, so let's move on to RAID 4. Where things get a little bit more interesting. So our goal, okay, so with RAID 4, right, so far we've only seen designs with redundancy that involve sacrificing at least 50% of your storage capacity to be able to recover from failure. Suppose that I don't want to waste 50% of my storage capacity. So what might I do? Right, so how could I use, right, less than 50%? So how could I use ideally, let's say, just one drive for parity? So suppose I have n drives, and my challenge to you is come up with a way that will only use one drive for parity, and we'll still be able to recover from any single drive failing. Does that challenge make sense? Does anybody have any suggestions? Or would anybody like me to kind of rephrase what I just said? Yeah.
One drive, like a parity bit, XOR memory hidden to the drive that go into the third.
Yep. That's basically what we end up doing here. And I'm gonna, okay, so let me break that down for you. But that was great. Did you know that, or did you just think of that? You knew that. Okay, well. Okay, So let's break this down. So we're going to use the XOR operator to do this. Have you all, I guess you've probably all seen the XOR operator before, right? So the XOR operator, right, when you take two inputs and you XOR them, you get, this thing called a parity, right? And what does XOR do, right? If, both bits in the input are 1, you get a 0. If one of them is 1, you get a 1. If both are 0, you get a 0, right? That's what XOR does. Now, an interesting property about XOR is, So an interesting property about XOR is that assuming we XOR two inputs, and now we have, right, the parity. So the parity is the result of XORing them. The parity allows us to recover any one of the inputs, assuming we have the parity and all the other inputs, except for, the one that we lost. Right, so in this case, suppose that, we have input 1. We lost input 2, but we still have the parity. Right? If we XOR those, if we XOR the input that we still have with the parity, we're going to get the input that we lost, input 2 in this case. Right? On the other hand, suppose that we lost input 1 and we have input 2, right? Again, if we XOR input 2 and the parity, right, we end up with input 1, which is the one that we lost. Okay. So how can we use this insight to design a RAID system? So can somebody kind of articulate that for me? What should we do? Yeah. Okay, yeah. And generally, however many drives that I have, right, I can have one drive that will just store parities. So this is basically, okay, so that was good. Another note about XOR, XOR is commutative and associative, right? So no matter how many inputs you actually have, you can still recover any individual input, assuming that you have the parity, right? Okay. So here's what we're going to do. Right, so we're going to take data from across the drives. So here, yeah, so here's basically what this looks like. Here's our address space from before. We're going to do basic striping across 3 of the drives. Right, so so you see these 3 drives, they store data. This drive just stores parities. And we're doing striping across these, and we're doing striping because striping is, it's good for performance, right? It allows us to get fast sequential throughput. Right, so we're striping here across 3 drives, 0, 1, 2, 3, 4, 5, 6, 7, 8, right? And for each one of them, we're storing the corresponding parity on the parity drive. And right, each one of these, right, each one of these represents a page address, right? It represents let's say a 4 kilobyte chunk of data, right? So in practice, I take 3 one-page chunks of data at a time. I XOR them, and I just store the XOR page, right, in the parity drive. So does everybody kind of get how this works? Okay. Okay. So now here's an interesting challenge. How might I do an update? So, okay, suppose that I have a sequential update. A sequential update is kind of easy, right? Suppose that the user is trying to update addresses 0, 1, 2. And that, I get that request to update all 3 of them at the same time. That's an easy case to handle, right? I can just rewrite them, right? Rewrite 0, 1, and 2 on each of these drives. Because I have all the new data at the same time, I can also generate the new parity for that at the same time and just write that on parity drive. Okay, so sequential writes are easy. But suppose that I have random writes. So suppose the user is just trying to update, let's say, address number 4. Right, so it's trying to update the page that's over here. Okay, but given that it's going to update page 4, right, I have this parity here. This parity relies on the old value of 4. So this implies that I need to also, what do I also have to do? I also need to somehow update the parity. So what's going to be my strategy? What would be, okay, so we're going to look at 2 algorithms here. One of them is naive and maybe a bit slower, and one of them is a little bit smarter. Those of you that think that you have a smart solution, keep your hand down for now. Those of you that think that you have like a very, kind of naive solution, maybe voice that out first. So yes.
Just take everything out and do one again.
Okay, so you're saying read everything again
Yeah.
and store it again, right?
Yeah.
Okay, so I have this 4 here, right? And I want to update it. So as you say, I'm going to read pages 3 and 5, store them, and rewrite the parity. Excellent. That's exactly the naive solution that I was looking for. What would be our cost analysis for this kind of solution? ON, yeah, it's kind of ON with respect to the number of drives. We can be a bit more precise, right? So, okay, so this is the solution, right? The solution is just, right, I have the new address of 4 here. I'm going to read page 3 and 5, store them, and then write, the new parity on this parity drive. And this is the cost. And so if I have n drives, I have to do an additional n minus 2 reads, right? Because I have to get all the other addresses like to kind of reconstruct the original stripe. And then I have to do 2 writes, right? One to the drive where the page that I want to update actually resides, and one update to the parity drive. Now, how can I, okay, so that's the naive solution. Does anybody have a suggestion for a smarter solution? One sec. Okay, so yeah, over there. So say that again. Yeah. Okay. Okay, so that's exactly the right intuition. So how would you use that, and what would you do with that in practice?
For like how it's changed, or like whatever it's changed.
Okay, so these are the right intuitions, but it's still not, you're still not giving me exactly concretely like the action steps. Like what do I need to read from where? So over there. Yeah, so I think you're saying the right thing. Yes. Okay, so what we can do, I think this is what you said, right? So we can take the parity, take the original parity, just read that instead of reading all the other, right, all the other pages. So we're going to read the parity, and we're going to read the original value of 4, and we're going to XOR them. And in some sense, like sorting them, like so just like taking this 4 old and storing it with the old parity, that negates the original influence of XORing 4 into the parity. Right? So now once we've negated that, we can XOR in the new value of 4, right? And then write that back to the parity drive. Okay, so what's going to be our analysis for this solution? Yeah. Constant time is correct, but be more precise. What are the constants? So how many reads do you have to do, and how many writes do you have to do?
Reads 2 writes.
Yep, exactly. Right. So okay, I mean, I guess this slide probably gave it away, right? You have to do 2 reads here. So you have to do a read to the original drive and the parity drive, and then we have to do 2 writes, one to the drive you're trying to modify, and one to the parity drive. Okay. So far, so good. We're actually going through this lecture awfully fast. I want to slow this down a little bit, otherwise we'll finish early. But what's the problem with this so far? Yes. Excellent. That's a great point. We're not going to solve that problem for now, but this is a problem that grade 6 and higher levels of grade actually do try to solve. And how would you imagine that they solve that problem? More parities, exactly. Right. So instead of having one dedicated parity drive, they might have multiple ones. And in fact, they're going to use more sophisticated codes, more powerful codes. Right. So I think so. Hamming codes or Reed-Solomon codes might actually get used, but these are more sophisticated schemes that we're not gonna use here. But I think even in the context of okay. Anyways, that's all I'll say about that. Okay, so that's an excellent point. We cannot using all of these schemes that we've seen so far, like using RAID 4 so far, we can recover from at most one failure. If two drives fail at the same time, tough. We have to use a more advanced version of RAID. What's another problem? One sec. Yes.
If data is corrupted, then maybe we lose the backup as well.
Okay, but that's kind of the same problem, right? The problem is that we can recover from at most one drive failure, but if two drives fail simultaneously, we're screwed.
No, I'm saying that if one of the drives, the data is corrupted, the one becomes 0 or something.
You're talking about like some sort of random error?
Yeah.
Okay. Yeah, I mean, so yeah, so if one of them, if you have a random error, you probably need a more. Well, if you have a random error, I'm not even sure that RAID is the correct scheme to kind of fix that. I think to recover from like random bit shifts, you typically have like some error correction codes like within the database as well. Like, I think the operating system might also have these, right? So different errors can occur, different layers of, kind of the software stack. So here, I don't think RAID is actually able to fix random bit shifts. It's there to fix disk failures. But it's a very good point that different errors might occur at different levels. Okay, so still there's a problem here that nobody's articulated so far. Yes.
There's no parity. Cannot use like parallelism to improve this efficiently. Is that a problem?
You're kind of right. You're actually touching on a good point. So mirroring creates redundancy across drives. So mirroring is actually able to provide us with better random throughput, right? Because here you can have the case. So here, right, only one drive stores address number 3 and 0, right? So if I get two simultaneous requests for, maybe two addresses that reside in one drive, right? I have to serialize them. I have to do one and then the other, right? With mirroring, as you point out, if I have multiple requests that are, due to the same drive, I can actually parallelize them, right? So mirroring does give me better random output. That's a good point. This is a downside of these schemes compared to mirroring. That's a valid thing to say, but it's still not the problem that I'm looking for. So the problem that I'm looking for occurs when you have a lot of random writes. So when we have a lot of random writes, what bad thing might happen here? Yes?
The issue that it's basically, even if it's just like 2 extra writes, it's still adding a lot to like each write. So I can say like for each write, we have to do 2 more writes.
I mean, so that's correct. And it is kind of an annoying overhead, but let's assume that's kind of the best that we can do. So yeah. Okay, excellent. Yes. So, okay. So the parity drive can become a bottleneck for random writes. So to see this, I'd suppose that I'm trying to update different pages across different storage devices. For each update, I have to do one write to the drive that I'm actually targeting and one write to the parity drive. So basically, this kind of implies that everything becomes serialized and my random writes just end up with the kind of combined throughput of just what my parity drive can do. So that's kind of annoying. Does everybody get the problem? Okay. So how might we solve this problem? Okay, so I'm sure you know, but let's give another 15 seconds for people to think. Does somebody have an intuition of what you might do? Okay, what's your intuition? Sorry? You want to strike the parity drive? Is that what you said?
Yeah.
That's a very good idea. Any other thoughts? Yeah. Okay. So you actually said slightly different things, right? So one thing you can do is to strike the parity drive, and another thing that you can do is mirror the parity drive. If we were to mirror the parity drive, would we actually win? We wouldn't win. Why?
Because there will be like inconsistency between the two. Like if you try to update one, update the other, we have to fix that problem.
Yes, so we would basically still be at the combined throughput of just one of the drives, right? And this is because, right? So imagine that we have two different parity drives. Any change that goes to one of them also has to go to the other one. So I still can't really parallelize. Okay. Does anybody want to say anything else? Okay. But yes, striping the parity drive is exactly the intuition that leads us to RAID 5. Okay, so with RAID 5, right, we're going to again do striping. So far we're the same as RAID 4, right? We just take these addresses, store them across the last drive. So how about the next addresses, 3, 4, and 5? What should we do for those?
Scrap it and put the parity bits to another tier.
Okay, correct. So now I'm going to take pages 3, 4, and 5, and I'm going to put 5 here now, right? But the parity is going to go over here. You seem impressed, but it was kind of your idea, so. Okay, and this continues, right? So 6, 7, and 8, right? Again, 6, and now we put 7 and 8 here, and we put the parity here, right? So in some sense, the parity is starting at the end and traveling backwards. Right, and then the end, 9, 10, 11, the parity is now at the first disk, and then we start over. Questions, thoughts, feelings? Okay, so RAID 5 summary. So this is a scheme that does not waste most of our storage capacity, right? We're still only using one drive for parity. So that's pretty nice. We are doing sequential writes at almost the combined capacity of all the different drives. Right, we're still basically using one drive's worth of bandwidth, but we're pretty close to the maximum capacity. How about sequential reads? A sequential reads damaged, or are they okay? Yeah. Yeah, basically. I mean, so sequential read. Okay, sorry. So this point is not about sequential, but sequential reads are still actually going to be at the combined throughput of all the drives, right? And again, this is because of the reordering trick that we've seen before. Okay. So this is the point that you brought before. So random reads indeed have less flexibility than if we were to use mirroring, right? Because mirroring gives us the flexibility that, if one drive is targeted by multiple requests, right, we can kind of distribute them. So there is a disadvantage here. We're not going to be as good at random reads, but perhaps nothing's perfect, right? So there are always trade-offs. Yeah, sequential reads are as fast as possible. And a random write now requires 2 reads and 2 writes. Right, so I think this is kind of the complete summary. Okay. So yeah, so then what if two or more drives fail at the same time? This is exactly the point that was brought before. Okay, so the thing to note about simultaneous drive failures is that if you have a lot of drives in your data center, simultaneous drive failures that can actually become quite probable. Right? Imagine that you have an array of hundreds of disks, or I don't know how typical that is, but maybe tens of disks. The probability that any two of them fail at the same time is actually not that negligible when we're talking about many drives that are just running for a very long period of time. Okay, so tips. Okay, so in practice, you probably want to do something else. You probably want to have multiple parity drives. That's going to help you against multiple failures. So if you go into more advanced kind of arrays, which we're not covering here, right? There's a nice theory about exactly how much parity drives you need to be able to recover from different numbers of drives failing simultaneously. Okay, so we finished a little bit early. I will be here for questions. Yes. So actually, let's just quiet down a little bit because I couldn't hear the question. Yes, what's the question again? Sorry, I still can't hear you. Speak up.
When this fails, you can recover it. You read every other disk.
So when a disk fails, you have to read all the other. Oh yes, that's an excellent point. Actually, yes, you do have to. So with RAID 4 and 5, if a given disk fails, you basically have to do a combined scan of all the other drives to regenerate that disk that failed. Yes. Any other questions? Okay. So today was a Friday. Usually we have tutorials on Fridays. What I will actually post some examples of tutorial questions from this week that we don't have time to do them live. From next week, so next week on Tuesday, we're going to start looking at databases. So we'll look at buffer pools and we'll look at row stores, how to actually structure tables. And then next Friday, we'll actually get into how we normally do tutorials and we'll do problem solving. But for this week, I will still post tutorial exercises on the course website, and it will give you examples of the kind of questions and answers we typically do in tutorials. All right, thanks very much. I'm here for office hours.